So that's weird. Why did I go back to that? All right. Good morning, everyone. So, as a reminder, last class, we finished all the material that we needed for testing, for test 2. And as I said, this one's a little bit more of a piecemeal, or whatever you want to call it, because we didn't do a lot of chapter 2, and we skipped some sections in chapter 3 as well. And we've said several times that if we have time at the end, we'll come back to it. We don't really anticipate that happening with the pacing of this course, having to miss a class, and then we're still like an hour behind in another class, arguably, but it's fine. I make sure that we get all the necessary techniques for anything that you would have in, say, your economics classes or your accounting classes that would actually involve the calculus. So we make sure you get the calculus. Maybe we just don't get to the extended concepts is all. So your homeworks should all be set up appropriately. And then your test. So we said that the tests always come in general a week after the material is finished, unless we don't have that option, which that can happen for test 3. We'll find out at the end. So 1, 2, 3, 4, 5, 6 sections. It's going to open up at midnight on Friday. So this Friday the 3rd, because we finished the material on Thursday, last Thursday. And then you'll have Friday, Saturday, Sunday, Monday. So that's 4 days total. One of those is a holiday. So I still give you the 3 days I said I would give you. If you're someone who doesn't mind working on the morning of 4th of July or something like that, before you go and have fun, you got that option too. But I won't force you to work on 4th of July. And then it'll close out Monday the 6th by 11:59 p.m. 9 p.m. The review, I just started piecing this together last night. I will finish it after a class and I'll have it up. I'm hoping to have it available by about 3 p.m., but I will definitely have it no later than 5 p.m. So it'll be very similar to last time. About the same number of questions as the test, which I don't have the number of test questions on the top of my head. I don't think it's going to be 20, as I said last time. I'm thinking more in the ballpark of like 16, 15, just depending on how I pick my questions, how I choose my questions. And then you have your homework due dates as well. So no surprises here. And with that being said, oh, and the test itself will work just like last time. You'll get 2 attempts, 2 hours each. Best attempt is graded. Work must be submitted in Canvas. So there'll be a spot to submit your work in Canvas, just like there was for test 1. And that's how, if you deserve any partial credit, that's how you will get it. It does this to me. Word is silly. There we go. What was I saying before I got distracted? 2 attempts, submit your work in Canvas. So like if you think you deserve 3 or 4 points on a question that was worth 5 points, I mean, you can't tell me how many points you deserve. I determine that, obviously. But if you think you could get some partial credit, you can shoot me an email. Hey, Mr. Beckner, can you check out questions 12 and 17? And then I'll go to your work. And if I see good work, then I get partial credit. But remember, if you type in, say, 12 as your answer in the test, and you have your answer as 9 in your work with no actual work, I just see a 9, that's not going to get you credit. I have to see work that shows that you actually got the answer. I think that's all I really need to say about the test. You should be familiar with the format. I'm pretty fair with this. People did pretty good with the round 1 test, round 1 test, if you want to call it. So hopefully the same goes with test 2. People have been keeping up with their homework mostly well, so I think this will be okay. But the problems are a little more extended. This these first derivative tests, second derivative tests, optimization, there's a little bit more depth to it. It's not just apply the product rule, apply the quotient rule, apply the chain rule. There's more going on. All right, so I'm going to quit rambling, and we're going to go ahead and get into new material. So this material will not be on the test 2. It will be on test 3. And with this chapter, just like the last couple chapters, we will kind of piecemeal this together. We won't necessarily cover every single topic. For instance, 4.2, we're going to use as an introduction to a concept, but I'm not going to assign you formal homework on 4.2, and I don't anticipate testing you on 4.2. But but the concept of 4.2 is important. So I'm still going to cover it as a concept, but moving forward, the problems are extremely time consuming to do in that manner. So I just don't really see the need to do it in this course. Again, unless we have time to come back to it at the end. And as many times as I've said that, we're not going to be able to come back to all these topics. So anti-differentiation. Another word for anti-differentiation means anti-derivative. It means the opposite of a derivative. Anti-opposite. Anti-opposite. So an antiderivative, opposite process finding a derivative. So I've alluded to this before. I've said there are 3 main topics in this course: limits, derivatives, and antiderivatives. There is another word for anti-differentiation and antiderivatives. Don't you love math people? It's not just us. It's science people in general. They like to have multiple words for things. And believe it or not, it's not just them as well. The English people, oh man, they got 50 words for different things, right? Synonyms and homonyms, oh my, all that good stuff. So one more word for this stuff is integral. Integrals are antiderivatives. They are the process of anti-differentiation. So we define lowercase w and an n before that. We define the indefinite integral as the antiderivative of some function f of x. So up until now, if I gave you the function x squared, you could find its derivative, and it would be 2x. Now what we're going to be doing is going backwards. Now, with anti-differentiation, with antiderivatives, with integration, you'd start with the 2x, and you'd say, okay, what's the antiderivative, or what's the integral? And then you'd say x squared, because they're just going backwards. If x squared has a derivative of 2x, then 2x has an antiderivative of x squared, ... There's actually some more to it than just that, and we will see why that is soon enough. But if you start with one function and you take its derivative to get a second function, then if you start with the second function and antiderivative it, you get the first function, basically. So, notation. This is important. If you're given some f of x, so given some function, this is the symbol for an integral, or this is the symbol for an antiderivative, or anti-differentiation, whatever you want to call it. This represents the integral of a function. So the integral of f of x times dx. What is this thing? Just go with it for a minute, we'll get into it. But really, this right here is all we're really worried about. This dx is just always going to be sitting there. So the integral of some little f of x, we tend to denote this with a capital letter. You don't have to, but this is typical. But then there's also this, plus a c, where the c is a constant. So I'm just going to flat out give this to you and then explain why. So the integral of some function, and again, this is just an extra little detail, kind of like dy dx is a derivative. This is just part of the integration process. You got to get used to the symbols. Again, this is really what we're focusing on. And this symbol, this little like snake looking S thing on the left and a dx on the right, that's us to do an integration, to integrate, to derive, whatever you want to call it. It would be equal to some function plus a constant. Some function plus a constant. But this is if and only if. IFF, this means if and only if. Mathematicians love this phrase because it means it's a two-way street, not just a one-way street. If is only a one-way street. If and only if is a two-way street. It means it works both ways. So if and only if the derivative of the thing on the right is equal to the thing on the left. So again, just kind of making a note here. Usually denote the integral with a capital letter of the original. Typical, doesn't have to be. I could say, instead of writing the capital F, I could write a G, a lowercase g even. But then this would be a lowercase g prime equals f of x. So the integral of function 1 is equal to function 2 only, so if and only if, the derivative of function 2 is function 1. The integral of function 1 is equal to function 2 if and only if the derivative of function 2 is function 1. Let's try this out. So, for example, the function f of x equals x squared, let's go back to what we were talking about earlier, has a derivative of f prime of x is equal to 2x. That's just using the straight up power rule, which you should all know, should all be embedded in your brains from now until eternity. Drop the exponent down, then decrease it by 1. So if we start out with the function x squared, its derivative is 2x. This says, or so, the antiderivative integral of some function 2x of this function is f of x equals x squared and then plus c. Now I didn't use the capital letter this time because I already was using the prime notation I was showing. Function, derivative. So here's the original derivative and then here's the original function. So if I wanted to just switch the letters, I could say it. Or if I called g of x equal to 2x, then capital G of x, this is the integral of 2x dx, which is x squared, plus this constant. Again, derivative going from x squared, you get 2x. If you go backwards, starting with 2x, you get x squared. But then there's this extra constant in there. But why is c there? I don't have enough space for the question mark. Let me do this. Why is there a constant there? Some number, a 5, a 12, a 39, a negative, a million, pi. It's just saying that some number is going to be there, potentially. Check this out. Let's say your original lowercase function is x squared plus 9. This has a derivative of f prime of x equals 2x. Say f of x equals x squared plus 100. This has a derivative of f prime of x equals 2x. Say your function was x squared plus 209,111. The derivative of that is still just 2x. Notice when you take a derivative, of a constant, it goes away. So, all right, before we get to the so, if your function was x squared, its derivative is 2x. If your function is x squared plus 9, its derivative is 2x. If your function is x squared plus 100, x squared plus a million, x squared plus 209,111, all of them have the exact same derivative. So when you're working backwards, if you've got the derivative and you're doing an antiderivative, we know that the 2x leads to an x squared. Because, I mean, just look, every time we've had x squared, it led to 2x. So going backwards, 2x leads to x squared. But how do we know whether it has the 9, the 100, the 209,000, a million, or nothing? We can't, let me type this part. I'm getting sick of that. We can't tell what the antiderivative has for a constant based on the original derivative, because when you take a derivative of a constant, it is 0. This is why we have the plus c. That plus c just denotes that, hey, at least for now, given the information we've talked about thus far, when you go to do the antiderivative, you can't say definitively for now whether that function had a 9 at the end, or 100 at the end, or a 209,000 at the end, or nothing at the end. So you just put a generic plus c in there to say, hey, we don't know what the number is, but maybe we could find it later. Maybe there's a way that we can find that later. And by maybe, I mean there's definitely a way we can find it later. Now here's what sucks. In your homework, if you forget the plus c, it's wrong. On a test, if you forget the plus c, it's wrong, but if you show your work, I could go back and give you partial credit. Now remember, this is test 3 material, so don't focus on this too much for now. But again, without a plus c, your answers are wrong, and you'd have to come back and say, if it was a test, hey, check out my work. I had the main part of the antiderivative correct. I just forgot my plus c. Okay. Now, before we go to just going and giving you the power rule for integration, the power rule for anti-differentiation, those are the same thing. There was a power rule for derivatives, and there's a power rule for going backwards. But instead of going through and doing a proof of this, which we can't do proofs of antiderivatives in here, it's kind of crazy. So we're not going to worry about that aspect. But what we will do is try and find a pattern. So let's see if we can identify what a formula for a power rule look like by doing derivatives. So let's say if f of x, we already saw x squared led to 2x. So with a function of x squared, the derivative is 2x. With a function of x cubed, the derivative is 3x squared. With a function of x to the fourth, its derivative would be 3x to the third. With a function, let's skip x to the fifth, let's just go straight to like x to the eighth. Its derivative would be 8 times x to the seventh. Because when we go take a derivative, we bring the exponent down and decrease its exponent by 1. So doing derivatives, bring the exponent down and then decrease the original exponent by 1. We're going backwards. So going backwards, in other words, anti-derivative, backwards, not words, we need to do the opposite of these things. So we expect the exponent to increase by 1, and we need to eliminate the coefficient that may have been the original exponent via division. So again, imagine yourself going from the 2x to the x squared. What's happened? The x had an exponent of 1 and it goes to 2. How about this one? The x cubed goes to a 4. The x squared goes to a 3. The x to the seventh goes to an 8. So going backwards, each of these exponents is going to increase by 1. Instead of decreasing by 1, we're now going to increase by 1 because we're going backwards. Okay, well, how about the rest? Because let's go back to derivative mindset. With the x squared, the 2 drops down. With the x to the fourth, I wrote a 4 here. No one said anything, and that's okay. This is supposed to be a 4. 4, not 3. Let me erase that. If anyone wrote that, I'm sorry. Bring the exponent down, which was a 4. That was me rushing. And then decrease the exponent by 1, so 4 to 3. So with a derivative of 2x, the antiderivative is x squared. The 2's gone. But you can't get rid of this 2 by addition or subtraction. You got to get rid of it by multiplication or division. Well, it feels like it multiplied one way, so now to go backwards, we divide. So we'd have to divide it by 2. Or this one, we'd have to divide by 3 to get rid of the 3. This one, you'd have to divide by 4 to get rid of the 4. This one, you'd have to divide by 8 to get rid of the 8. How do we know what we're dividing by? We're dividing by what the future exponent is. So again, in order to get rid of this 2, you divide by 2, which is the next up exponent. To get rid of this 3, we divide by 3, which would be the next up exponent. To get rid of this 4, we divide by 4, which is this exponent plus 1. Divide by 8, so there's no 8 here anymore, which should have been 7 plus 1. This is what leads us to our formula by just observation. So, power rule for integration. Let's put all of that together. The integral. So this is the symbol for integral. And if you want to make it nice and pretty, oops, too much. It looks like that. When you're doing your work, if you're anything like me, they end up looking more like S's, and that's okay, like a backwards S, if you will. I don't know why I said backwards S. What am I thinking? Ignore what I just said. If I didn't mention this at the beginning of class, I'm teaching with one eye open right now. I've scratched my cornea. It's a lot of fun. So I might make one or two more mistakes than usual. Doing my best. Okay. So that's our integration symbol. Then the thing that you're actually going to go backwards on goes here, and then at the end is a dx. So we're doing a power rule, so that's an x to the n. Just like when we did a power rule for derivatives, it was the derivative d dx of x to the n. But then you put this little dx here. This is just part of the integration process. When you take a derivative, you divide by the dx. When you integrate, you multiply by the dx. That's kind of the idea of the opposite there, multiplying versus dividing. That's why there's a dx in a top instead of a bottom. There's no dy because this thing is basically your dy. Again, don't worry about that confusing idea there. So here we go. Here we go, here we go, here we go. Now when you actually integrate, this symbol is no longer there. Notice above, when you integrate, that symbol is no longer there. You just switch to a capital letter instead of a lowercase letter. So the exponent needs to increase by 1. So we get x to the n plus 1. If we start out with n, we have to add 1 to that. Divided by. Then we are going to divide by what the future exponent is. The n plus 1, this is the future exponent, so that's what we divide by. But then there is also the plus c. So what we're saying here is that little f of x is the x to the n, capital F of x is the x to the n plus 1 over n plus 1 plus the c. Or you could say f prime of x is x to the n, and then the regular function is x to the n plus 1 over n plus 1 plus c. That goes with the above. If I just do this, there we go. My squiggle looks a little off. Can I drag that? That looks awful. Everything just got squished on itself. I don't want to have that moved. Sorry. I'll rewrite that for the next time. These are all saying the same thing. The integral of x to the n is x to the n plus 1 over n plus 1, then plus a c. If you prefer to call the original function a lowercase f, when you integrate it, you call it an uppercase f. If you were given the original function written in derivative notation, or it could have been dy dx or df dx, then the function would be this. Again, you have to get used to the different ways you can see this. If you're given it originally as a function, the integral is a capital F. If you're given it originally written in derivative notation, then the integral is just a regular function, no capital that time. Check this out. Take the derivative of the right-hand sides. The x to the n plus 1 over n plus 1 plus c. Let's take the derivative of that. So d dx, all of x to the n plus 1 over n plus 1, then plus c. Well, derivative means take the exponent, drop it down. This n is not an x and this is not a variable. These are representing numbers. There's no implicit differentiation here. These are numbers. So we drop the n plus 1 down in front. Then we have to multiply that by the x. We're going to decrease the exponent, n plus 1 minus 1, divided by, now you might notice this is a terrible looking product. We have to wrap it in parentheses. That n plus 1 is still on the bottom. then there's the plus. The derivative of a constant is 0. The n plus 1's here cancel, so that's just an x. The plus 1 and the minus 1 cancel, so we get x to the n. QED, that means quod erat demonstratum. It means proof, proofed, done, finito, finished. So now that we have our power rule, let's try it out. Again, this right here, this is the main version of it. I'm not going to leave the highlighting there. I'm just highlighting it for a second. Add 1 to the exponent, divide by the same new value, not the original value, the new value. Example 1. Find the integral of the given f of x. So again, that doesn't say find 5 times f of x times dx. This is the integral symbol. I just want you to go ahead and get used to me writing it a little sloppy because I usually don't take an hour to write that. This is what it comes out to. So for a, I'm going to give you an original function of x to the 5th. So x to the 5th is our original function, and we're going to find its antiderivative. We're going to find its integral. This is the process of integrating or anti-differentiating. They all mean the same thing. So in red, we'll do the integral of x to the 5th times dx, which, by the way, the dx, this is known as a differential. And no, not the differential of a vehicle. No, not a differential like a differential diagnostics in medicine. This is for math differentials. Differentials relate to derivatives. We're going backwards. This right here is just letting us know what the variable we're integrating over is. Kind of like when we had the dx in the bottom, that let us know what letter we were taking a derivative with respect to. So this is kind of like our with respect to. So if you had mixed variables in here, which we can see in later chapters, and we will, it tells you how you're actually processing this. Do you care about the x's or do you care about the y's? All right. So here's what we do. This is a power rule. So the x stays. The exponent, we add 1 to the exponent. That's what n plus 1 means. Add 1 to the exponent. So 5 plus 1. I'm writing out all the detail this time. Divided by. Divide by literally the same value you just wrote. 5 plus 1. But don't forget your constant at the end. 5 plus 1 is 6, so this is x to the 6th over 6. I got a little crazy with that division bar. Plus c. This is it. That's the answer. Or you can write it as 1 over 6 times x to the 6th plus c. Why did that happen? There we go. That's the same answer. X over 6 is the same thing as 1 over 6 times x. My math lab should not care which way you write it. I will not care which way you write it. But if you said it was 6 times x to the 6th, that would be wrong. If you don't believe this, you can take the derivative and you should get the original problem. If you drop the 6 down, so in a different color, and this is going to be the only one I check, take the derivative of what you got as the answer, x to the 6th over 6 plus c. You bring the 6 down, so that's 6 times x. Decrease the exponent by 1, so it's now 5. Don't forget that there was a 6 in the bottom. The derivative of a constant is 0. These 6's cancel. You get x to the 5th. It works. As I said, it's the only one I'm going to check. but you are always more than welcome to check. Let's try another. And let's go ahead and get weirder with this. F of x equals the square root of x. We're going to find the antiderivative of this. Now remember back in the derivative sections when we dealt with square roots? What did we have to do? We never had a square root rule or a cube root rule. We had the power rule. We had to switch this to its other notation. So you need to remember that the square root of x is equal to x to the 1/2. The index becomes the denominator, the numerator is the power originally. So the integral of the square root of x dx is equal to the integral of x to the 1/2 dx. If you don't do that, you can't move any further. So now we apply our power rule. Remember, the power rule just basically says add 1 to the exponent and divide by that same new value. Add 1 to the exponent, divide by the same new value. The exponent is originally a half, so maybe you need to say, well, what is a half plus 1? Because that's what's going to be coming up. We have to take that 1/2 and add 1 to it, divide by the same value. Take a half and add 1 to it, but don't forget to add the constant. So those half plus 1s, that's a half plus 2 over 2, which is 3 over 2. You've got to be down with your fraction arithmetic or you're going to have problems. So 1/2 plus 1 is 3/2. So this is going to be equivalent to x to the 3/2 divided by 3/2. This is a compound fraction or a complex fraction, depending on what name you like. They're not allowed. So we've got to adjust this. And we move on, right? There's nothing else after this. Wrong. Plus c. So again, as a reminder, a over b divided by c over d. This is the same thing as a over b division symbol c over d, which is a over b times d over c. You flip it and change from division to multiplication. That's how we divide by a fraction. You multiply by the reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. So x to the 3/2 over 3/2 plus c is the same thing as x to the 3/2 times 2/3 plus c. But we don't like a normal product like this to be variable then constant. We want the constant first. So put the 2/3 in the front. This is our antiderivative. This has the x to the side of the fraction. It could also go in the top. So you could go 2x to the 3/2 over 3 plus c. Now, I have these boxed up, but I really don't like these answers. I don't like these answers because the original problem was in radical form. So me personally, I prefer my answers in radical form, but I know that my math lab very often allows this to happen, especially when these are in the denominators. But they're not, so I'm going to say it's much better to switch back to radicals when appropriate. So that says the integral of the square root of x dx is equal to 2/3 times the denominator is a 2, so that makes this a square root. The numerator is a 3, and I'm talking about the power, not the 2/3 fraction. I'm talking about this 3/2. This denominator is a 2, so it's a square root. This exponent's power is a 3, so that's a 3 inside. So that's 2/3 times the square root of x cubed plus our c. This is the best answer. Again, the square root could be to the side or to the top. When I say best, I just mean it's better to have radicals than the rationals. So there's a little more going on with that problem, so let's review. Radicals, calculus, always got to be turned into rational exponents. That's got to happen at some point. Then we apply the power rule, which is said add 1 to the exponent divided by the same value. We did our fraction math. But then because we had divided by a fraction, we had to multiply by the reciprocal. This is an old rule. Everyone needs to know that, which turned this into 2/3 x to the 3/2 plus our c. But then we said, because this is pretty easy to switch back to the original notation, let's do so. So the x to the 3/2 became a square root of x cubed. If this had been x to the 2/3, this would be the cube root of x squared, but it's not, so it's not. So this is a great problem. Any type of radical problem is great. You can handle anything like the 5th root of x to the 9th, the 17th root of x to the 3rd power. I don't know, all those you can integrate. Let's do another one. C. Let's find the integral when our function is equal to 1 over x squared. So we're doing the integral of 1 over x squared dx. So here's the function, and then we have the times the dx. Now, note, this is equal to the integral of dx over x squared. If you multiply the 1 and the dx, you don't really need the 1 in the top. These are one and the same. I don't care which way you write it. You need to understand that they're one and the same, though, because you might see it this way, or you might see it the other way. So be prepared for both. I don't always just give you the function and ask you to do this. Sometimes you're just given the problem straight up. In fact, this is how I usually just go ahead and denote things. I usually don't give you the function and ask you to find the integral. I usually just say, find this integral. I might write it in the left way. I might write it in the right way. And I don't mean right as incorrect. I mean right-hand version. All right, well, we know our power rule. Power rule says add 1 to the exponent and divide by the same value. But here's the thing. Look where that x is. It's not in a denominator. It's in a top. We had the same issue with regular derivatives back in weeks ago. So when the variables were in the bottom, we had to bring them to the top. Guess what we're going to have to do here? You're going to have to bring the variables to the top. So this x squared, when you bring it to the top, you change the sign of the exponent. Excuse me. In fact, I got a cough pretty bad. I'm going to mute for a second. All right, much better. So we get the integral. Now the x squared comes to the top. If it was a positive 2 in the bottom, it's a negative 2 in the top. Do I really need to write this 1 times x to the negative 2? Do I really need that 1? No, so I'm not going to write it. I'm just going to write x to the negative 2 dx. The dx is always in the top. It never goes to the bottom. Leave it alone. So what we do is, now I'm going to integrate. If you do this, if I do this and x to the negative 2 plus 1, this is wrong. because I still have that integral symbol here. This is so common. When I learned calculus, guess what? I did it a couple times. When I'm in class watching students, guess what? Somebody's doing it. When I give a test, guess what happens in the answers? I see this in the answer every now and then. When you actually go through and change your exponents and do whatever formula you're applying, this symbol shouldn't be there anymore. So it's equals. No more snake S thingy anymore, just X. Add 1 to the exponents, that's -2 plus 1. Show your work for this because sign math is hard sometimes. Then divide by the exact same thing as the new exponent, which is -2 plus 1. And we add our C. Now -2 plus 1 is not -3. That is the most common mistake people make. It's -1 all over. -2 plus 1 is also -1. There's a plus C. Dividing by -1 is the same as multiplying by -1. So we don't want to leave that in there. We generally don't like negatives left in denominators. If this was a 2, you could leave the 2. If it was a 5, you'd leave the 5. But the negative really needs to come in front. Dividing by 1 does nothing. So this is -x to the negative first plus C. But this is bad notation for an answer, and my math lab generally will not accept this. Negative exponents are not very sane. They're not very normal. You need to bring this variable back to the bottom, just like we were doing with derivatives, and change the sign of the exponent. Now that negative, this negative is still in the front. So that's what I just wrote here. That's the negative. Now this x to the -1 is going to become a fraction, and the x to the +1 goes in the bottom. We still have our plus c to the side. There's nothing written in the numerator, which means you need a 1. Now this 1 we typically don't write. We typically don't write 1s for exponents because then they look like primes, and I'm not taking any more derivatives or anything like that. This is just the answer, 1 over x, with the negative in front. So -1 over x, then plus c. Let me just move that. Equals -1 over x plus c. The negative can go on the top, or it can go in front of the fraction. Shoot. So either of these is okay. But having the -1 as an exponent, this is not okay. You cannot leave that in an answer. You have to simplify that. Again, if you don't trust this, do the derivatives. Everything will work out and you'll get your original functions. The derivative of the constant will always be 0. The derivative of that primary term will always go back to the original function we had. Now, I need to point out something. The rule that we wrote earlier for the power rule is incomplete. This power rule right here is incomplete. There is a detail that is missing that I am now going to cover. So let's just do an asterisk here. Weird. What happens if we try the power rule on f of x equals 1 over x? So check this out. Integrating 1 over x dx. Bring that x to the top. So this is the integral of x to the -1 dx. The exponent was originally a +1, so now it's a -1. Now we can actually do the integral. We add 1 to the exponent, divide by the same value. So we go x to the -1 plus 1 over -1 plus 1. Don't forget the plus c, which is -1 plus 1 is 0. So that's x to the 0. Ooh, that was terrible looking. Over 0 plus c. Anything raised to the 0 power is just a 1. That's 1 divided by 0 plus c. But anything divided by 0 is undefined. Now here's the thing. There is an antiderivative to 1 over x. There is an integral of 1 over x. But when you try to do the power rule with this, it fails. The reason it fails is because when there was a positive 1 in the bottom, that makes it a negative 1 in the top as an exponent. When you add 1 to negative 1, you get 0, and you can't divide by 0. So this is a problem. The power rule does not apply with exponents of negative 1. When your x is in the top, if the exponent's a negative 1, you cannot apply the power rule. So I'm going to go back to the power rule. You all need to go back to your notes and adjust the power rule. And you need to make a note that the original n cannot be negative 1. The original n cannot be a negative 1 because when you add 1 to it, you get 0, and then you're dividing by 0, and kaboom, the world blows up. Bad things happen. That doesn't say that there's no antiderivative for this. There's a formula for it. And in fact, if you think carefully to the only 4 or 5 formulas we really gave you for derivatives, there was a derivative that had an answer of 1 over x. We'll get into that shortly, though. We want to do some other problems first. So more on this later. Sooner than later. So right now, all we have is the power rule, and we have one minor exception that the n is not allowed to be negative 1. There was no exception like this for derivatives because we were bringing exponents down, and that was never going to be an issue of dividing by 0. But when a formula involves dividing by something, it's possible that this bottom could be 0, and that's only possible if the original n was negative 1, because negative 1 plus 1 is 0. So that's why there's an exception to this case. Again, we'll come back to what really happens with this integral. We don't use the power rule. There's a formula. We'll come back to it. Again, that formula is spoiled based on the derivatives. But for now, let's talk about the sum and difference rules as well as constants. So constant integration will be here. Remember, if you took the derivative of a linear term, you got a constant. So the derivative of a constant, and I'm going to use the letter a since there's going to be a c somewhere. The derivative of a constant, so the integral of a, and then this is the dx. Again, this is just part of the notation. This is the function right here. That's a constant. A number. A is a number. This is equal to ax plus c, where again, a is a number, as well as c. It's a constant. So the integral of 7 would be 7x plus c, because the derivative of 7x is 7. You can also say, ah, shoot. You can say, ah, shoot. No. Forget it. Oh, it worked that time. I don't understand Word. Sometimes that works, sometimes it doesn't. Okay. In general, what if you have the integration of a constant times a regular old function? Remember how when we took a derivative, the constant in front didn't really matter, you just multiplied it out? Guess what? Same thing. The integral of some a times a function is just equal to a times the integral of the function. In other words, the constant is just a multiplier. Like with derivatives. Now this is super general. This doesn't just say the power rule. This says the integral of any function times a number is just the number times the integral of the function. And we will see that applied shortly. Also the sum and difference rules of integration say just like derivatives, These do not affect formulas or outcomes. In other words, the integral of some f of x plus or minus a g of x, no matter whether it's a plus or minus, is just the integral of the first function, the first thing. Then you can add or subtract the integral of the second thing. Just like with derivatives, this is not true for multiplication or derivative or divisions. And you know what kind of sucks? While we had a product rule and a quotient rule for derivatives, there's no true product or quotient rule for integrals. We have a lot of different scenarios that we have to kind of be careful with and play our hands appropriately. We will get to that much later. So just like if you have the derivative of x squared plus 5x, you can take the derivatives of those terms one by one. If you have the integral of x squared plus 5x, you could take the integrals one term at a time and just throw in the appropriate signs as needed. Okay, let's try this out. Example 2. Once again, find the integral of the provided function. For A. Sorry, my dog is distracting me. Come on, buddy, stop it. The integral, or sorry, let's have our function be 3x squared. Hold on. All right, my dog kept licking my feet. He had to move. Fun times. The integral of 3x squared plus 10x minus 7. There's our function. That's an ugly 2. So here's our original function, and we're doing the integral, not the derivative, the integral. We're going backwards, using new formulas, new ideas. And you might be saying, why would we ever want to do this? Don't worry, we'll get there. So the integral of, and because there's multiple terms, you have to wrap it in parentheses like so, 3x squared plus 10x minus 7. This could have been how I originally gave you the problem. I can give you the problem written just like this in red, or I can say, find the integral and here's your function. Or I could say, here's your f prime, find f. Or I could say, here's little f, find big F. Those would all be the same problem. So these pluses and minuses don't really affect anything. You can just think about these integrals of terms one by one. The 3 and the 10 in front don't affect anything. You just leave them attached. So you can show the really meticulous work of this, which I will never, ever, ever do again. This is the integral of 3x squared dx plus the integral of 10x dx minus the integral of 7 dx. This is the fancy way of doing things. And then you can bring the 3 and the 10 in the front. So 3 integral x squared dx plus 10 integral x dx minus integral of 7 dx. You don't have to write things that way, though. Most people know they can go straight from the first to the last. So whether you do this writing or not, I don't care. Just understand that the 3 stays there. Then we add 1 to the exponent and divide by the same value. So x to the 2 plus 1. I'm going to keep showing this work for a while. divide by that same value, 2 plus 1. Then a plus. Leave the 10 there. Then we have our x. Now there's no exponent written, so we have to assume that it's a 1. We don't like writing 1s because they look like primes, though. So we don't write it. So the original exponent was a 1, and we're adding 1 to that. Divide by that same value. Divide by 1 plus 1. Minus. Now this is just a constant. There's no x's. We said up here that the integral of a constant was just the constant times the variable. So minus 7x. And if you stop here, you're wrong, because we need the constant of integration. That's what this C is called, the constant of integration, or integration constant. But we can definitely clean this up some. In the bottom, in the bottom an exponent, 2 plus 1 is 3. In the bottom an exponent, 1 plus 1 is 2. So this is 3x to the third divided by 3, plus 10x to the second divided by 2, minus 7x plus c. The 3 and the 3 here cancel, and you get an x cubed. The 10 and the 2 here divide, and you get a 5. So 5x squared. The minus 7x stays, the plus c stays, and there is our integral. And if you do the derivative of x cubed is 3x squared, boom. The derivative of 5x squared, bring the 2 out, 2 times 5 is 10, 10x, boom. The derivative of negative 7x is negative 7, the derivative of a constant goes away. So again, sums and differences do not really affect the rules for integration. Constant coefficients do not really affect the rules of integration. This is a great simple example to demonstrate that. And remember, if you ever don't like something, if you're not sure about something, when you're integrating, take the derivative. If you get the original function, then you're good. Let's do another. 3x squared. Let me write that this is f of x. I forgot that part. F of x equals 3x squared. Oh, I'm sorry, you said that one. Flip the paper, Rodney. X to the fourth. Minus 6x cubed. This is what happens when you're teaching with one eye. Plus 5x minus 1. We want to find the antiderivative. We want to find the integral. So what we're doing is integral symbol. Multiple terms, so it needs to be in parentheses. Let me show you what it would look like without the parentheses, in fact. So let me just write, I'll leave the space for it. X to the fourth minus 6x cubed plus 5x minus 1. And then you have your dx at the end. Now this dx is supposed to be multiplied by the whole function. This is only multiplying the dx and the 1. These are the only two things linked together. So this is very, very bad notation, which is why you have to wrap your function in parentheses for integrations if there's multiple terms. When in doubt, use a parentheses. Okay. All these are polynomial terms except for the constant at the end. So all of these, you add one of the exponent divided by the same. For the constant, we just get an x next to it. So with x to the fourth, add 1. I'm going to stop showing the adding 1. 4 plus 1 is 5. So that's x to the 5 over 5. Again, this number and this number should always match when you're integrating. Minus, leave the 6 alone. Have our variable, add one of the exponent. 3 plus 1 is 4. Divide by that same number. Plus symbol. Leave the 5 alone. Then we have our variable. Add 1 to it. There's no number written here, which implies that it is a 1. 1 plus 1 is 2. So that becomes 5x squared over 2. Again, these numbers match. These numbers match. These numbers match. minus the integral of a constant, just slap an x next to it. So 1x. I'll write the 1 here, but I won't in the next step. And then don't forget your plus c. Let's clean this up. X to the 5th over 5, nothing cleans up. That's x to the 5th over 5, or 1/5 x to the 5th. Minus the 6 over 4 reduced to a 3 and a 2. And this would become a 3. This would become a 2. I don't want to leave that written there. So that's minus 3 in the top, 2 in the bottom. Then we have our x to the 4th. Then plus the 5x squared over 2, nothing happens there. Minus the 1x, we don't need to write the 1, and we leave our plus c there. And again, you can write it this way, or you can write the variables to the side. So that would be 1/5 x to the 5 minus 3/2 and x to the 4th plus 5/2 and then x squared minus x plus c. Both of those answers are 100% acceptable. Sometimes you'll see things written the left way, some the right way. You got to be prepared for both. Let's do another. Lots of repetition since this is new. Let's have our original function be y to the 4th. Let's and since I'm going to do y's, this needs to be an f of y. Sorry about that. So we're going to do an f of y is going to be y to the 4th plus the 4th root of y. Now, because these variables are y's, when I do my integration, I'm not going to do the integral of dx, even though I know the original instructions said that. We're going to integrate this over dy, just so these letters match. They don't always have to match. We'll get into that in a later chapter. So y to the 4th plus the 4th root of y. Well, we're going to have to change the 4th root of y, aren't we? This is going to be the integral of y to the 4th plus y raised to the 1/4. The 4th root of y is y to the 1/4. The exponent was a 1, the index is a 4, 1/4. All right, well, that's good enough. We can apply the power rule. Add 1 to the exponents, divide by the same resulting value. So that's going to be y to the 4 plus 1 is 5, divided by 4 plus 1 is 5, plus, let me do this work to the side at least for the fraction. So note, 1/4 plus 1 would be 1/4 plus 4 over 4, which is 5/4. Come on, select. Why aren't you selecting? That was weird. It's Word. Shouldn't be surprised. So adding 1 to 1/4 is 5/4. So this will be y to the 5/4 in the top and then divided by 5/4 in the bottom. Plus c. Okay. Y to the 5th over 5, nothing happens. But we're dividing by 5/4. Dividing by a fraction is the same as multiplying by its reciprocal. And I'm going to go ahead and put that in the front. So dividing by 5/4 is the same as multiplying by 4/5. Again, this is 4/5 because this was 5/4. Dividing by 5/4 is multiplying by 4/5. We saw that demonstrated back up here in blue. Dividing by a fraction is multiplying by its reciprocal. Then we have the y to the 5/4, then our plus c at the end. Now, MyMathLab might be okay with this. I'm not really, because that 5/4 you need to switch back to the original notation, in my opinion. So this is y to the 5th over 5 plus 4/5. That's the fraction in front. Because the denominator of the exponents of 4, this will be a 4th root, because the powers of 5, the numerators of 5, excuse me, the powers of 5. And then we have our plus c. This is the answer in the best notation. Remember when we were doing derivatives of radicals, the radical index generally didn't change? Guess what? Still true, because you're adding or subtracting 1, denominators aren't going to change. So if you start with a 4th root, you're going to end with a 4th root. If you start with a 17th root, you're going to end with a 17th root. It's the powers inside that typically change. Now, I'm not going to say there aren't exceptions to every rule, but this is just generally what you'd see. Somebody's got their mic on. If you don't mind, please and thank you.
It's called roses. I'm sorry, roses.
You got your mic on. Whoever's talking about roses. There we go. All right. I muted you. I wish I was able to have everybody be able to talk to me in class, but I know that half of y'all got stuff going on just like me. Fortunately, with me, it's just dogs, and I can make them shoo. So again, the pluses and minuses don't really affect the outcome of an integral. Constants in front of variable terms don't really affect the outcome of an integral. But we said earlier that multiplications and divisions, there's no product rule. There's no quotient rule. You can't just take the integral of the top and the integral of the bottom and slap them together, or the integral of the first thing and the integral of the second thing and slap them together. And you might say, well, let me do the first times the integral of the second, then plus the integral of the first times the regular second, and try and like manipulate the product rule of going one way to another way. It doesn't work that way. Now, what's interesting is one of our techniques for products involves kind of what I just said, but very rearranged. Again, another day. But for now, what happens if we do see a product? So example 3. I'm making this a new example because it's different, but at the same time, it's the same. So we're going to find the integral of f of x dx. And this time, I'm just going to go ahead and write the function inside of it. So here's our integral symbol. And we're going to have an x cubed times 4x to the 5th plus 2x dx. Now, this is written as one big product, so this is perfect notation. I don't have to say, write a bracket around this stuff. I don't have to do that. You might see it that way, but you don't need it. This is fine. If this x cubed had a plus here, then this would not be fine. It's not, that's a times. So this is a product. There is no product rule. So for now, just try distributing. So this will be equal to the integral. X cubed times 4x to the 5th would be 4x to the 8th. X cubed times 2x would be 2x, so plus 2x to the 4th. 1 plus 3 is 4. And then we have our dx here. I distributed, so I don't really need the parentheses anymore, right? That's usually what happens. And yeah, in algebra, that's fine, but now we got this extra little dx thing that is still supposed to feel like a product of everything else. So even though you distributed, you still need that parentheses. It kind of feels unusual, but you get used to it. Such is life, right? Now we can actually apply the power rule. So if this was something that had to be FOILed, you'd need to FOIL it out. If it was even worse than that, for now, you'd have to do that multiplication. Spoilers, again, it's like the 4th time I've mentioned this, later it's not always going to be so clear cut. We'll have techniques for them. So equals. Now I'm integrating, so I don't write this symbol anymore. I don't need that anymore. I'm going to apply the rules. Leave the 4 in the front. For the x to the 8th, add 1 to the exponent. 8 plus 1 is 9. Divide by the same value. 8 plus 1 is 9. Plus symbol. Leave the constant coefficient in front, so plus 2. Add 1 to the exponent, divide by the same thing. So that's now x to the 5th, and divide by 5. Then don't forget our plus c. 4 and 9 don't reduce, 2 and 5 don't reduce. This is the answer. That's it. You missed the c, you're wrong. If you subtract the exponents instead of adding, you're wrong. If something could be simplified and you don't simplify, you're wrong. Please be careful. You're going to be testing in a few days on derivatives. You are not being tested on this. So when you're doing power rules in this upcoming test, don't add 1 to the exponents. You're going back to subtracting them. When you take test 3 of the final, I can give you an integral, then a derivative, then an integral, then a derivative. You've got to pay attention to the instructions. Pay attention in which direction you're going, because that is extremely important. Don't just think, oh, I'm going to always subtract 1, I'm always subtracting 1, I'm always subtracting 1, or I'm always adding 1, always adding 1, always adding 1. Problem 2 doesn't have to be anything like problem number 3. Doesn't have to be like anything like problem number 4. Pay attention to the instructions. Have your rules in order. Practice, 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 practice. How many hours a week? 8, 9, 10 hours a week outside of the lecture is what you should be dedicating if you still struggle. If you master it in 4 hours, you only got to do 4 hours, right? All right. So that is enough with the power rule. But guess what? We had rules for taking a derivative of exponential and logs. Guess what? We also have rules for taking integrals of exponentials and logs. So let's get to these other types. Oh no. Come on, quit this. Frustrating. I don't know why I can't just insert a page after that. Get it? Draw, erase. Sorry about this complication. I thought I gave myself enough space and I didn't. So this integral was 4 x to the 9th over 9 plus 2 x to the 5th over 5 plus c. There we go. All right, other rules. Specifically, exponentials and logs. Exponentials in the e base, the integral of e to the x is e to the x. This only works if the base is e, just like the derivative only worked if the base was e. The derivative of an exponential was itself, as long as the exponent was just a plain x. We had that chain rule that got involved with it as well, but for now, we're just going to keep the exponent simple. We'll play with that soon enough. In fact, let me go ahead and do that. So this is the first version of the rule. Or the integral of e to the ax dx. We're only going to give you one very simple version of this for now. This would be 1 over a times e to the x plus c. e to the ax plus c. So the first version is if the exponent is just a plain Jane x. Honestly, we won't see that a lot. This version is if there's an extra constant in there. And honestly, this just kind of follows from the chain rule of derivatives. When that happened, you took the derivative of the exponent here. So this is like us undoing it with the division, just like we divided by the n plus 1 with the power rule. So this is only a linear term. If this is an x squared, we don't know what to do for now. If this is an x cubed, we don't know what to do for now. This is just a 5x or a 7x or a 12, things like that. Then for our natural logs, we have that the integral of something, I'm going to leave this something blank for a second, equals the natural log of the absolute value of x, and of course plus the c. And I'm trying to exaggerate the absolute value parts because of the L and Ln. We had a derivative of the natural log of x before. d dx of the natural log of x was 1 over x. So guess what? The integral of 1 over x is the natural log of x, basically. Remember I said earlier that power rule had that weird special case that you couldn't let the exponent be a -1? When the exponent's -1, this is what you fall into. Now that's not the integral of a natural log. That's an integral leading to a natural log. The integral of 1 over x dx, or dx over x, is the natural log of the absolute value. This absolute value is often not written if the problem claims x is bigger than 0. That would make the absolute value pointless to say. If you say that x is positive, you don't need to take the absolute value of a positive. It's positive. But here's the problem. If I don't somewhere say that x has to be positive, we're allowing x to be negative when you can integrate it. But if you remember how logarithms work, you can't have non-positives inside of a logarithm. This x has to be positive, or the inside has to be positive. But if this x over here is negative, if this was just a regular logarithm, now you've got a negative inside of the logarithm, and you're breaking the rules. So this is kind of a weird issue. If the problem says that you're only dealing with positive x values, you don't need the absolute value. But if it's just a very generalized problem, which is more often what you'll see, you need the absolute value. And let me tell you, this is what students forget. Because you don't need it for a derivative, but you need it for an integral. It's subtle, subtle differences. And I would say probably half the time you're told that the x is positive, which means you don't need the absolute value. But then the other half, you're not told that, and you do. So you just have to understand the context. You have to understand when you need it. Me personally, I always use it because even if we're told that the x has to be positive, this is still true. So this is the n equals -1 case. You might say, well, I don't see a -1. It's right here. This is an x to the +1. When you bring it to the top, that's your x to the -1. So when we tried to do that with the power rule, this was the integral of 1 over x. We brought the x to the top. The -1 causes 0 in the bottom, and the world imploded on itself, undefined. Now we know that the integral of 1 over x dx is really the natural log of the absolute value of x, or the natural log of x if x is positive. Integrals of exponentials is as easy as a derivative of an exponential. The integral of a 1 over x is the natural log of x because the derivative of the natural log of x is 1 over x. Let's try these out. What do we have to? Example 4? Yes. And once again, we're going to find the integral of f of x dx. A. The integral of 7 over 3x dx. There's an x in the bottom. There is only an x in the bottom. It does not have any other exponents. This is that special case. This is not the power rule. If this was an x squared in the bottom, power rule. If this was an x to the 5 millionth, power rule. Because it's an x to the positive 1 in the bottom, this is not the power rule. This is the one and only one time you can't use the power rule. We have to use the natural log rule. But there's this 7 and 3 in there. If you don't understand that these are just going to be multiplied by the answer, you can show your work and bring them out of the integral. This is me saying the 7 and the 3 do not affect the integral. They're just constant coefficients. But now there's a 1 in the top because the 7's not there anymore. There's still the x in the bottom and the dx. Now, I never said anywhere x is positive, so I need the absolute value. The 7/3 just stays there. This right here, this integral would be the natural log part. So times the natural log, and if I do this, it's wrong. I'm missing the c. I got to have my constant. And even if I do this, it's wrong, because once again, I never said x is positive, so we need the absolute value. Because with 7 over 3x, your x is allowed to be any number except 0. So it could be negative 1,000,000. But if you put negative 1,000,000 here, you're taking the natural log of a negative, and you can't do that. So this is our answer. So let me show you what I'm saying. So I'm going to do a versus, and I'll do this in blue. So let's say the problem was this, 7 over 3x dx, where x is positive. So then when you integrate, you have your 7 over 3 integral 1 over x dx. And again, if you don't need to show this middle step, you don't have to. Me personally, I go straight to the end. I just say, oh, I have a single x in the bottom. That's that weird exception to the power rule. When I get a natural log, the 7 and the 3 just stay out front. So 7 over 3 natural log of x plus c. I don't need the absolute value because I was told x is positive. When you put positive numbers in an absolute value, there's no effect. So these are two slightly different versions of the same problem. One has no restrictions, the other does, which means one has an absolute value and the other does not need it. And I believe in my math lab that if you wrote this as the answer to the second one, if you put that absolute value in there, I think they mark it wrong because you're not being specific enough, because they gave you the restrictions you should know to cut that out. So please be on your toes there. Let's do another. Let's do the integral of 1 over 8x. Now when I say 1 over 8x, that x is in the bottom. If it was in the top, this would not be the same problem. If it was to the side, this would not be the same problem. If that was an x squared in the bottom, or any exponent, this would not be the same problem. So this is very similar to the last one. If you need to pull the 8 out, you can, and you don't even have to pull it out of the integral. You can do it this way and make your conclusion, or you can do it, some people will just do it this way, 1 over 8 times 1 over x dx. Some people take this extra step. That's fine. It's just extra work though, it's extra writing. That's not an x on the top, that's a 1. Oh, my hurts. Dx. And right here, here's that special case again. When you integrate a 1 over x, you get a natural log with an absolute value unless you're told x is positive. The 1/8 just stays out in the front. So 1/8 times the natural log, absolute value of x. And if you box this up, It's wrong. What did I forget? Forgot my plus c. So I left that space there. Again, there are going to be ways, there are times when you can find the c. The problems I've given you so far, you can't find them. You have to be given what's called an initial condition. You have to be told some function value under the integral in order to actually find the c. So there are problems where we can find the c. I have not done any of those yet. All right, problem c, as opposed to the integration constant c. The integral of 5 times x to the negative 1 dx. Now you might say, oh, x to the negative 1, power rule. If you go and try the power rule with this, negative 1 plus 1 is 0, you're going to be dividing by 0 and the world blows up. No. So it's actually interesting. This is the one time where you want the x in the bottom. This is the one and only one time you want the x in the bottom to make it look more familiar. So we go integral 5 over x dx. Negative 1 in the top, positive 1 in the bottom. If you need to pop the 5 out, that's 5 times the integral of 1 over x dx, which is 5 times the natural log of the absolute value of x, plus our c. And that's it. D, the integral of e to the 2x dx. We did a bunch of the natural log ones. Now let's do an exponential. So going back above, we said the integral of e to the x is e to the x, just like the derivative of e to the x is e to the x. But of course, the plus c is thrown in. If you have an extra coefficient with your x, you just divide by this value. And again, I kind of gave you this as a leap of faith, but I did relate it to the power rule, how we divided by that number in the exponent. When the exponent was n plus 1, we divided by n plus 1. When this exponent has an a times the x, you divide by the a. All right. So because this has a 2, when we actually do this integral, we need to divide it by 2. So we go e to the 2x. Let me pick my right color, though. So I am integrating. No more integral symbol. And I can't just go plus c. This is wrong. This is wrong. Wrong. Because this 2 is here, I need to divide by that. And if you prefer to write this as 1/2 e to the 2x plus c, both of those are accurate. There's nothing else you can do here. If you don't trust this, do the derivative. When you take the derivative of an exponential with a complicated exponent, it's the derivative of the exponent times the exponential itself. The derivative of 2x is 2. This 2 times this half will cancel, and it'll give you a 1, and then you still have your e to the 2x. It does work. Again, try that on your own if you're not sure. E, the integral of 8 e to the 4x dx. That's a 4. So the 8 doesn't do anything. Just leave it out front. Times. Because the exponent has that 4 there, we're going to have to divide by that same value. We don't add 1 to it. We just divide by that same value because we don't change the exponents of exponentials. So we'll have the times e to the 4x, but then we divide it by 4. Then our plus c. The 8 and the 4 reduce to a 2, though, this time. So that's 2 e to the 4x plus c. So that one, there was a reduction, unlike the previous example. One last one. Oops. the integral of 5e to the negative 3x. Now I might say, oh, negative exponent, bring it to the bottom. Definitely not. If this e was in the bottom, you'd bring it to the top, no matter what the sign of the exponent was. The 5 does nothing. Leave it out front. Because this is a negative 3, that's what we'll have to divide by. So times e to the negative 3x divided by negative 3. Don't forget the negative. Then the plus c. 5 and negative 3 aren't going to reduce, so let's just make that a single fraction of negative 5/3. And then the e to the negative 3x plus our c. Again, if you don't trust any of these answers, take the derivatives. You will get the original functions if you know how to take your derivatives appropriate. We have time. All right. So let's do another set of examples and let's complicate things a little. That was example 4. We're up to example 5. And this time I'm going to change how I write the instructions, but it's literally the same thing. I also want this in black. So we're going to say, given f of x, find capital F of x. So little f of x for a is going to be equal to negative 4 x to the negative 1 plus 3 x to the negative 2. So because we're told we're given a lowercase letter and asked for an uppercase letter, that means we know we have to do this integral. There's multiple terms, so wrap it in parentheses. Now, what I love about this problem is it's a mixture of the power rule and something else. It's set up to look like it's just power rule, but this is the third time we've come across this. If you add 1 and negative 1, you get 0. You're going to be dividing by that same value, and you blow up the world. So the first term is going to end up being dealt with like that natural log. The second term is a straight up power rule. So this is a mixture of ln's and power rule. You got to know which one's which. So the first one, we want this to look more like the logarithmic rule. So this is going to be the integral of negative 4 over x to the positive 1. Then for the second term, that's going to be 3. You do want that exponent in the top. We can't power rule the first term, which is why we bring the x to the bottom. So that way it's set up like the natural log rule. We can power rule the second term, though. So this negative 4 in the top, all that is a constant coefficient. With an x in the bottom, your integral is a natural log of an absolute value of x. Then plus, leave the 3. And we're going to add, this is going to be a power rule, so we add 1 of the exponent. Please note that negative 2 plus 1 is negative 1. So this 3x to the negative 2, we leave the 3. The exponent becomes a negative 1, that's us adding 1 to it, and we divide by that same value. And then we add our constant at the end. Well, that's negative 4 times the natural log of the absolute value of x. Dividing by a negative 1 just says to change it to a subtraction, so minus 3 x to the negative 1 plus c. But this is not a regular format for an answer. We don't like negative exponents in answers. So this is negative 4 times the natural log of the absolute value of x minus 3 over x. The x goes to the bottom, but not the 3, plus our c. And what I find is fascinating about this problem is, remember how we did derivatives of derivatives? If you integrated an integral, if you integrated this one, this term ends up being a natural log. And we don't even know how to integrate this term yet because we don't know how to integrate a natural log yet. We'll find out later. We can integrate and get a natural log, but we don't know how to integrate a natural log yet. Let's do one more problem and call it a day. I don't want to get into the next section since we're about to test, and I don't think we have to. This is going to be the integral. It's going to be a big fraction, x e to the x, then a plus 1 all over x, and then dx. I don't need a parentheses. I do want this fraction bar to be a little smaller. Didn't need it that long. I don't need a parentheses since this is a big fraction, multiplying the dx. As long as the dx is to the side. If I wrote the dx in the top, I would need the top in parentheses. Well, this looks like a product, this looks like a quotient, and I said there's no product or quotient rules for integration. There's no straight up product rule, there's no straight up quotient rule. Now, last time when we had a product earlier today, like example 3, we just distributed it. So this time when we got a quotient, maybe we should just go ahead and do the division. So let's split the fraction. Oh, and by the way, the answer to A, I said find f of x, capital F of x. This was the capital F of x. I forgot to write that. So this time, our little f is the inside, and the big F will be the answer. So if we split this up, here's what we get. The integral of x times e to the x over x. That's the first term over the denominator. Then plus the second term over the denominator, the 1 over the x. But now I do need this wrapped in parentheses with a dx because of the multiple terms written that way. Multiple fractions, it looks different. Well, guess what? In the first one, thankfully, because this looks like a nightmare to integrate with the x's there, they all cancel. So this is just the integral of e to the x plus 1 over x, and then all dx. Again, the thing on the left and right is just the notation. Inside the parentheses is what we're actually integrating. Well, the first bit is literally a formula. The second bit is literally a formula. The integral of e to the x is e to the x. The integral of 1 over x is the natural log of the absolute value of x. You're supposed to memorize those. If you box this up and ship it out, you'll get it wrong, though, on your homework. And you'd have to point out that you did that on a test for me to give you more points, because you got to have your plus c. You don't need a plus c for each term, because if you have a plus c here and then a plus c here, those constants can just be added together to make a new plus c. Like pretend that the first c is a 7 and the second c is an 11. Well, 7 plus 11 is 18. Why not just have a brand new c and call that the 18? Adding a bunch of arbitrary constants just becomes a single arbitrary constant. So these are the very basic rules of integration that we will use for the rest of the next several chapters, in fact. We will keep extending on these concepts. We're going to apply this geometrically, just like when we did derivatives. We talked about how it was the slope of a function at any point. These integrations, these antiderivatives, have a very important geometric representation. So if you graph a function, its integral has to do with the graph in a similar way that if you graph a function, its derivative has to do with the graph. Derivative is the slope at a point, and integral is something else when you talk about graphical. We're going to start seeing these things, this little S snake curve, whatever you want to call it, with numbers up here, like you might have this be a 5 and this a 1, and we'll see what happens when that goes on. But for now, we'll call it a day. We'll say that is 4.1. I'm not going to make that homework due in a week, though, since we're taking a test right now. So let's see, we're testing, what was that, from the, oh shoot, the 3rd through the 6th over the weekend. So let's say that that next homework is due on the 9th. So 4.1 will be due on the 9th. I'll give you a little extra time on that because I don't want you focusing on integration yet right now. I want you focusing on the material that relates to test 2. So if you don't have any questions, we're going to call it a day there. I'll get that homework put in. I might not even get to it today. I might get that to that Thursday. So I don't know if I even want you to have access to it yet. I want you to start focusing on this. So when I get in class, I'm going to eat some lunch. I'm going to finish building your review, and then you should see it in in my math lab no later than 5 p.m. Hopefully by 3 p.m. I should be able to have that done because I've got about half of it done already. The test, again, will be posted by 12:01 a.m. on Friday the 3rd. It will close out after 11:59 p.m. on Monday the 6th. So you cannot work on this test on Tuesday before class. That will be impossible. It will be done. Make sure you get it done. Everyone did pretty well that took the test last time. I hope that that continues to be the trend, and I hope that everyone takes the test. Hint, wink, nudge. All right, have a good one. Take it easy. I'm going to go rest my eye for a while, get some lunch, and then finish y'all's review. Yes, and then we'll see you on Thursday. Email me with any questions. Take care.